Oh yeah, welcome back to Gallant Tutorial Academy. We are really excited to having you back here once more. So if you are new here, you know the right things to do. Ensure you subscribe, ensure you like, our video, share, and click the notification bell, right, as we drop new videos every week, right? So ensure you click the notification bell. So thank you once more. So in my last video, I actually explained to you all what chemical bonds were all about, right? I established the fact that chemical bonds are mostly found within atom and can also be found between molecules and compound, right? So who can actually remind me the types of bonding we have? Can you try? Alright, so I actually told you all that there are actually two types of chemical bond, which are interatomic bond and intra-atomic bond. So intra-atomic bond and intra-atomic bond. So this video is not actually for revision purpose or whatsoever, right? We actually came up with the initiative of treating some questions with you all, because once you're able to know the kind of questions they can ask or have a glimpse of questions that can be set on a particular topic, in short, you will definitely ace the examination. You definitely ace your examination, right? So this video do justice to that. So I actually spoke more on two particular topic, right? Two particular categories, which are ionic bond and what? Who can remember the second one? Covalent. So these are the two I'll be discussing: ionic bonding and covalent bonding, right? Just for a recap, what are ionic bonding? Ionic bonding has to do with is the kind of bonding that is witnessed when electrons are actually transferred from metals to what? Non-metals. Why covalent has to do with sharing? Covalent has to do with what? Sharing. It's actually nothing. It's not something hard, right? So but I'm not explaining, this video is not meant for that. So if you really want to know more about covalent bonding, ionic bonding and covalent bonding, to be precise, then refer back to our video. Now let's start. The first question says, ions have noble gas electronic configuration, right? And this statement was suggested by who? That was the question is all about. So who said ions have noble gas electronic configuration? Who said so? It was actually Kusel, right? Kusel actually said, he brought an hypothesis that said ions have noble gas configuration, right? So the correct answer here is simple, which is what? Kusel. But now, this won't profit you much. What exactly are ions? What do you understand by ions? Okay, I forgot to tell you that if you have if you're watching our video, ensure you interact with it. And it's not because we gain from that, it's simply because it's profit you more, right? When you interact with video, you learn more. Okay, when I ask a question, just comment in the comment section, right, and answer the question. But if you are not watching it live, some people would like to download the video and watch it later, something like that, then ensure you are writing down. When I ask what are ions, interact with it. That's how you learn. Do you understand that? I'm very sure that you will be the best in wherever you are found. You will be distinguished from others, right? So what are ions? Ions are actually formed from atoms, right? So from atoms. How are they formed? They are formed when atoms loses or gains electron. Loses or gain electron. So that's how ions are formed. Can you see the connection now? Can you see the connection? So ions are actually formed when atoms lose what? Electron. So I'm going to use an example that every one of you knows about, so you will to understand it. I'm going to first of all use Na, which is what? Sodium. Smart students. What's the atomic number of sodium? 11, of course, right? 11, of course. So this is how it goes. How does the ionic, how is an ion of sodium represented? Can anyone remember? Okay, it's represented as what? Na plus, something like this, something of this nature, right? Something of this nature. So, but how did he appear here? Like, how did he reach this state? He's reached this state by losing one electron. Do you get that? That's why it has plus here. That's why there is a plus here and not what? A minus. Now let me explain further. Now let's assume the electronic configuration of this is what? 281. This is the shell electronic configuration. But we are talking about the main electronic configuration to be 1s2, 2s2, 2p what? 6 and 3s1. Is that clear? Something of this nature. But I prefer using this. So in the course of this video, you will notice I use this more than the rest because it's kind of easier, right? It's kind of easier, but I'm just giving you this so you have an idea of it. So now, if this loses one of these electrons, it simply means that the proton will now be more. Remember that this is actually what? A neutral atom. I hope you know that. It's actually what? A neutral atom. And what does neutral mean? No charge. When there is no charge, it means what? Is what? Neutral. It's as simple as that. Okay, but when it loses one electron, that is, at this stage, there are just 11 proton. There are just 11 proton and 11 electron. That is at this stage. But when one electron is lost, it now becomes 11 proton and what? Smart students, and 10 electrons and 10 electrons. Do you understand that? That means this has more power than this. Therefore, there will be a positive charge here. Do you get the logic now? It's actually very, very straightforward. So now, this is not the key. I'm just trying to build a foundation. Good. So let's go to question again. Ions have noble gas electronic configuration. Now, what are noble gases? What are noble gases? Noble gases are the gases found in the 8th group of the periodic table. They are gases found in the 8th group of the periodic table. And why are they called noble? Just like now, halogen. Halogens include chlorine, fluorine, bromine, iodine, astatine, and the rest. She understand. So why are they called halogens? Because they are salt formers, right? Alkaline metals. They are called alkaline metals because they form alkaline or hydroxide easily, or they form soluble base, something like that. I guess so. Noble gas. Why are they called noble gases? Now they are called noble gases because number one, they are gases. They are gases. So number two, they are what? Noble. So what do you understand by noble? Noble is actually an English word which means something like respectable, right? Yeah, noble, respectable. But in this context, it means something like stable. Do you get that? So stable gases. So noble gas, instead of me calling them noble gases, I can actually say stable gases. Is still the same thing, nothing much. Do you understand that? Good. So why are they called stable? They are called stable because they hardly perform any reaction. Have you ever seen maybe sodium and argon? So just like now we have sodium chloride. So again, have you ever seen when we have maybe sodium argon? Nothing like that. I get it. There is nothing as such. And why is that? Because argon or noble gases are highly stable. They hardly enter what? A chemical reaction. And there is one special feature they have which gives them that special ability, and is what? Octet and duplet configuration. Octet and duplet configuration. Good. What does octet mean? When they say octagon, it has to do with 8 now. You get it. So now, what is a duplet? Duplet. Think. 2. It has to do with 2. So whenever the valence electron, right, that is electron in the valence shell is 8, is regarded as what? Octet. And when the valence shell is 2, like when the electron in the valence shell is 2, is regarded as duplet. And it's only helium that is in this category. Do you understand that? It's only helium that is in this what? Category. So atoms generally, whenever they have octet and duplet configuration, they are stable. Do you understand that? They are stable. So we will be able to establish what ions are, what noble gases are, and what electronic configuration is really all about. So we understand what Cosell is really trying to say. But I would like to add a simple thing so you'll be able to understand in case you don't really know it. Now let me use argon for example. What's the atomic number of argon? Definitely what? 18, isn't it? So we have 2 8 this 10, right? 288. So can you see it? If it's helium, which is 2, right? Just 2, duplet, octet. You get it now? You get logic. So it's not something hard, right? It's not something really hard. Very simple and straightforward. Do you understand that? So now back to this part. When it loses one electron, that is, ions have this. They become noble gases. No, not like they become noble gases. They obtain noble gas electronic configuration, right? Atoms obtain noble gas electronic configuration when they become ions, right? Look at this. It loses one electron. So this one is no more there again. Cancel it. This is no more there. What's this? 8. Is that not clear? That's what? Octets. Very simple and straightforward. Any question? If there's any question, please comment. We'll get back to you, right? And also I forgot to mention that if you have any topic you would like us to explain, do not hesitate at all. We are here to serve you, right? Comment, please. We would like you to produce a video on so topic, and we'll do justice to that. We love you, definitely. All right, second question. Pairs of outer shell electrons are not used, which are not used in bonding, are called what? First of all, let me explain what this shell is all about. They've talked about it too much. This is the nucleus of an atom, right? This is the first shell. This can be the second shell. I'll use oxygen now, right? Oxygen in this case. So what's the what do you call it? Atomic number of oxygen? Definitely what? 8. So it becomes 2 6. 6 will be in the outermost shell, right? Good. So this how it goes. We have 1 2 3, right? 3. Let me just put it here. 1 2 3 4 5 6. Good. This is the shell configuration of oxygen. You see this last one here? You see this one? That's what they do call valence shell. That's what they do call what? Valence shell. Don't know, confused. And the electrons here are called what? Outer shell electrons or valence electrons. Valence electrons. Good. So they don't say pairs. When they're talking about pair, what do they mean? They mean something of 2 that have like 2 now, pairs of shoe. You understand? So they don't say pairs of outer shell electron which are not used in bonding are called what? So this question has to do with bonding. Now let me take a good example. H2O. So it's in line with what I'm saying here, right? H2O now. Good. So we have oxygen and hydrogen. How would they combine? Good. So now let me just write this here. You know that the shape of this is bent. So when constructing we must ensure that we certify that too. So what would be the valence electron of hydrogen? Only one now. Do you get all of this? Only one too. So during bonding, this will meet together, right? And why this will meet together? Exactly. Good. So this one and this are called bonding pairs or bonding electron. They're called bonding electron. But you see these ones here, this scapegoat, they are not doing anything. They are not doing anything at all, just to be looking. They are called what? Non-bonding pairs. Non-bonding pairs. Good. You see these non-bonding pairs, they call them a very special name. They got a very special name called lonely at the top. That is lone electron. Lonely at the top. That is lone electron. At least you remember Ashake lonely at the top. You remember lone electron. So lone what? Electrons. Do not forget it. Do not ever forget it. So non-bonding pairs are called what? Lone electrons. So what the or lone pairs, right? So pairs, they are called what? Lone pairs or lone electrons. So it's not lunar, not lunar. I intentionally put lunar. So you're not So the answer is what? D. D is correct. Is that clear? Let me read again. Pairs of outer shell electrons not used in bonding are called what? Lone pairs. Do not ever forget that. Now to the next question. Complete transfer of one or more electrons. So in this question they are really talking about transfer of electron. I'm sure that a smart student would have comment the answer right now. Transfer electrons. Good. So complete transfer of electron from one or transfer of one or more electron from one atom to different atom forms what kind of bond? You see, this metallic bonding is the kind of bonding found in metals. This kind of bonding is kind of bonding that is found it can be found in NH4, that is ammonium chloride, right? But I'll not talk about this and this. I'll talk about metallic bonding and coordinate bonding in our next video. So ensure you stay tuned. So I'll explain covalent bonding and ionic bonding for the sake of this question. Now whenever there is transfer of electron, the keyword being complete transfer of electron, do you understand that kind of bonding has to do with ionic bonding? And an example is this: NaCl, right? We have Na being Na, one electron outside, chlorine being 1 2 3 4 5 6 7. I hope you understand how I got it though. You know this is 281 now. This is what 287. She get because of this what 11 and this what 17. You get the point now. So now what really happens is that, you know, for them to be stable, this must have the valence electron here must what 8. Why this must what 8 too. So this one can either give the whole electron to this guy and become 8, right, or allow this guy to give him electron, right, so it becomes what 8. So now which do you think will be easier? What do you think will be easier? Which one do you think will be easier? Losing one electron or gaining 7 electron? Definitely losing one electron. You understand? So that's why whenever you're defining ionic bond, they always say the complete transfer of electron from metallic atom to what non-metal. That's the way they do define it, and they'll give you a complete mark. So it transfer from here to what? This point. Do you get the point? So that our answer here is what? Ionic bonding, right? This is the correct answer. Ionic bonding. What of covalent bonding? Covalent bonding has to do with sharing, and it mostly occurs between what? Non-metals. It mostly occurs between non-metals. Is that clear? Good. Now let's move to the next question. Octet rule is not valid for the molecule. Alright, so we have CO2 here, right? What's the central atom? Can you try? This is the central atom. So we have carbon, right? Which is what? 1 2 3 4. Remember it's 6, so it becomes 2, 4. 4 valence electrons. You get this is not normal 8, which is equals to 2, 6. Do you get the point? So we have oxygen at this point and oxygen at this point. Do you get the point? So we have 1 2 3 4 5 6, right? 1 2 3 4 5 6. You get, so they will kind of combine together. This is the bond, right, which is linear. So now let's check if carbon is happy, because they are saying where is octet rule disobeyed in this following question. They get it. So now here let's check it out. So this bond, you know, it's not oxygen that have it, neither is carbon that has it. Both of them have it. It's just like in a house now, you know, some of these guys in university, they'll just come together and rent a room. Like 3 guys that just come together and rent a room. It's not as if the first guy has a room, neither does the third guy or the second guy has a room. All of them has a room. You understand? So it's just the same way in this case now. It's the same scenario. Now this is 1 2, 3, 4, 5, 6, 7, 8. Now carbon is what? Happy. Carbon is what? Happy. What of oxygen? 1, 2, 3, 4, 5, 6, 7, 8. Right? This is also what? Happy. The same thing for this also. 1, 2, 3, 4, 5, 6, 7, 8. This is also what? Happy. So this, in this part, octet rule is obeyed. Now let's go to the second one, being H2O. Right? I've actually given an example of this. Right? Probably let's refer back to it. So you will to, I don't want to just write again. Okay? Okay. Look at it here. Okay, I'm not okay, look at this now. So now this is 1, 2. This is duplet. Right? Duplet. Right? All of this 1, 2. Also duplet. All of oxygen 1, 2, 3, 4, 5, 6, 7, 8. So oxygen here is what? Complete. So you can say that H2O obeys the what? The octet what? Rule. Is that clear? So this is also what? Correct. Now what of O2? Let's check it out. So this is also correct. Let's check it out. O2. We have oxygen here and we have another oxygen. Right? Just from here, just put your 1, 2 here. You get the point. Right? 1, 2, 1, 2. Like that. 1, 2, 1, 2, 1, 2. Right? It needs 2 electrons. So it must share 2 electrons. You get it? It needs 2 electrons to complete it now. Do you get the point? Like this 1, 2, 3, 4, 5, 6. So it needs 2 electrons. So it must share 2 electrons. It's just as if this is just like an investment. Invest 100,000, get 200,000. She gets so that it must give 2 electrons for it to be balanced. So now let's check it out. So 2 bonds will formed. She understand? 2 bonds will form between them. So it becomes 1, 2, 3, 4, 5, 6, 7, 8. This complete. 1, 2, 3, 4, 5, 6, 7, 8. This is also what? Complete. So for oxygen is also complete. So that the answer is already obvious, which is what? CO. So this is scapegoat. This is scapegoat. So CO. Now let me explain it in details. So you're able to understand it. So this is CO, right? Good. So carbon first, right? Good. So we have 4 valence electron, like 4 valence electron, and for it to be stable, it must also donate. It's not like doing. It must share 4 electrons. It must share 4 electrons. But here, look at what is happening. Just look at it. Just look. Now we have oxygen, and how many electrons does oxygen have? It has only 6. It has only 6 electrons. So therefore, it has what? Share electron, right? This and this. And now let's count it. Is oxygen happy? 1, 2, 3, 4, 5, 6, 7, 8. Right? Oxygen is what? Happy. But is carbon happy? No! Carbon is not happy. Look at it now. 1, 2, 3, 4, 5, 6. So octet rule is not obeyed in carbon monoxide. This is carbon monoxide, in case you don't know. Carbon monoxide. Is that clear? Please, if you don't understand, please comment. We're here to serve you. No, now next question. The nature of bonding. The nature of bonding in tetrachloromethane. ClCl4 is tetrachloromethane. Tetrachloromethane. Hope you know that. I've actually taught you all on how to name compounds and stuff. In case you are just new here, please watch our video on organic chemistry. Right, it will help a lot. So this tetrachloromethane, all this, who can try? This was calcium hydride, right? Calcium hydride. This calcium hydride. All right. So that's the fact. So I'm not here to teach you how to name actually. So now they're asking, what's the nature of the bond? What's the nature of this bond? First of all, if I even talk about the nature, I want to explain to you the structure of this guy, right? And also explain to you the structure of this guy, right? So now let's move on. So this will be the central atom. So C, this, then we have chlorine here, we have chlorine here, we have chlorine here, we have chlorine here. Why for this we have so we have chlorine here, right? So why for this we have C, right? We have Ca, then we have Hj, we have Hj. Good. So what's chlorine? Calcium, I mean to say. We have 20, right? Which is equal to 28 what? 2882. So it has only 2 electrons, 2 valence electron. So let's present a 1 1 1 1. Right? So it's easier for this guy to just transfer the electron to this part, right? And 1 electron here, transfer it to this part. Do you get the logic? Do you get the point? So it's actually simple as that. So there is actually a complete transfer here being metal and this being non-metal. There's a complete transfer from the metal to the non-metal. Okay, what of calcium? What of tetrachloromethane? How does it go? See this carbon. It has four valence electron, right? It has 4 valence electron. The calcium has 4 valence electron. Good. So what of the chlorine? It has 7 valence electron. This carbon, right? Chlorine has 7 valence electron. This will be 1, sorry. Yes. You get the point now. So there are two things can actually happen here. This one can actually donate its electron to this guy so that chlorine will be happy. But if it does that, it will be left with none. Do you get the point? It will be left with none. So it can't sacrifice itself that much. Okay, now let's assume this guy is generous. Now say, okay, no problem. Since you don't have the mind to give me everything, now let me help your life. Now if chlorine now say, okay, no problem, take my own, what do you think will happen? It will now become 1 2 3 4 5 6. It's not still complete. So the only thing that can happen here is what? Sharing. The only thing that can happen here is what? Sharing. Is that clear? Sharing of electrons. Now how does this sharing work? This one will say, yeah, bring your own salt, I'll bring my Maggi, I get to cook soup, and both of us to share it. You get the logic? So now it becomes 1 2 3 4 5 6 7 8. You get what? So chlorine is happy, all these guys are happy. I get it. And carbon is also what? Happy, because this is now 1 2 3 1 2 3 4 5 6 7 8. Do you get the point? So carbon is happy and chlorine is happy. So in this particular part, we have what is known as ionic or electrovalent. Ionic or electrovalent bonding. Why in tetrachloromethane we have what is known as covalent bonding, right? We have what is known as covalent bonding. Exactly. So now let's go to our option and pick the correct one. Electrovalent in both, no. Covalent in in tetrachloromethane, and electrovalent in this. This looks like the answer, but we're not sure yet. Now option C, electrovalent in this. No. So all of covalent in both, no. So what's the answer? Smart people. Option B is correct. Exactly. I think this is very clear. Now let's move to the next question. Tetrachloromethane is insoluble in water because of what? Now you see, tetrachloromethane, it shows it has implicated itself already. It shows you that it's coming from methane. It's coming from methane. So tetrachloromethane is formed through what? Substitution reaction, right? So tetrachloromethane is formed from substitution reaction of methane using what? Chlorine under UV light. I've taught you guys, and go and check the video on organic chemistry. So like that's how it goes. Is that not it? And remember, methane soluble in water? We don't know. because we have not actually probably have not encountered methane or so. But methane is actually derived from hydrocarbon. It's actually derived from hydrocarbon, and hydrocarbon are what? Non-polar compounds. Non-polar compounds. So hydrocarbons are non-polar compounds. First, now let's ask another question. What are non-polar compounds? I see of polar, non-polar. What do they even mean? Now I will explain to you using polar. When we talk about polar, we are really referring to pole, like polar from the word pole. So it simply means a compound with pole. This is just the layman understanding. Polar compounds are compounds with pole. What kind of pole are they talking about? Electric poles. Do you understand? So now, chemically, polar compounds are simply compounds which have two charges in one. Like I said, they have two charges in opposite side. That is, one part of the molecule is positive and another part is what? Negative. Example are water, NaCl. For instance now, NaCl. Now when they dissolve with water, what does it become? It becomes what? Na plus and N and Cl minus. You see this part and this part, they both originate from what? NaCl. Is that not true? Which is what? Polar. Why is it polar? Because it has what? Two charges. It has a negative end and a positive end, as simple as ABC. Is that clear? So you understand what polar mean, right? Now when I say non-polar, non-polar are compounds that does not have sides that are charged, sides that are what? Charged. That's what non-polar is really all about. Now they now asked, calcium tetrachloromethane is insoluble in water because of what? Is water polar or non-polar? Water is polar. Water is polar. Do you understand that? Why calcium chloride is what? Non-polar. Calcium chloride is what? Non-polar. And there is a testament. What is the testament? Calcium chloride is what? In this. They both connect. You get the point? They both what? Connect together. She understand now. And there's a principle that like dissolves like. That is, a polar solute will only dissolve in what? A polar solvent. You get that? A polar solute will only dissolve in a polar solvent. Is that clear? Good. So now let's check the option. I've actually touched several parts in one distance. Now let's check the option. Calcium tetrachloromethane is non-polar. Is that correct? This statement is true. And water is polar. This can be the answer, but we are not sure yet. Let's continue. Water is non-polar. How about now? Water is polar. So this is wrong. This is wrong in itself. This is wrong in itself also. What of this? Water and are both polar. Mba. No, mba. So our correct answer is what? A. As simple as ABC. Is that clear? Good. Let's move to the next one. We have a few questions to go. The rate of reaction of organic chemistry, of organic compound is low. Why? Due to what reason? That's what they are simply asking. Good. Now, when you talk about rate of reaction, what exactly are they talking about? They are talking about how fast a chemical reaction can proceed. Right? Can proceed. That's what they really mean when they are talking about how fast or the rate of reaction. So when you hear, they're not asking how fast rate of reaction are slow. Why are they slow? Simply because of their bonding. There's a kind of bonding that they have. Now it's very easy for you to dissolve salt in water. Do you get that? It's very easy for you to dissolve salt in water. Why? Because of the kind of bonding that it has. Now, in laboratory, if you have been to a laboratory before, you notice that there are kind of reaction that occurs so fast, and that kind of reaction is mostly between ionic compounds. For instance, now they may say, okay, you have silver chloride. For instance, now a solution of silver chloride, and now you are now told to add zinc. Do you get that? You are told to put zinc into it. What do you think will happen? A displacement reaction will occur. It's now become ZnCl2 exactly plus Ag. Exactly. She get. Let's balance the reaction. So some of this nature will happen. But if you notice, the way it's going to appear very, very fast. I mean, in milliseconds, it happens so fast. Why? Because it involves what? Ion. This is it involves what? Ion. Because this part is a polar compound, so it's like Ag plus and Cl minus. Do you get that? Something like this. So it occurs really, really fast. But for organic compounds, most organic compounds are derived from hydrocarbon. What did I say about hydrocarbon? Hydrocarbons are what? Hydrocarbons are what? Are mostly what? Non-polar. They are mostly what? Non-polar. And from experience, non-polar compounds or non-polar reactions, right? Non-polar reactions are slow. They are slow. Gone. Do you understand that? They are slow. So now they are asking the reason. You know the reason already. The rate of reaction are slow because of what? The covalent bonding. Because of what? The covalent bonding is as simple as that. Do you get that? So the rate of organic compounds is slow due to what? Their covalent bonding. Now to the next question. The valence electrons of representative elements are what? First of all, what are representative elements? We have to understand that first. So this guy is expressing a new terminology for us. What does representative elements mean? Now, each block of the periodic table are called different names. Here you get, each block of the periodic table are called different names. Don't worry yourself. I will present it here. But please do me if you will. Immediately I'm through this video, go back to your book and revise. It will be able to stick more. Now let me draw my miniature periodic table now. This is how my own periodic table looks like. Okay. Yeah, I'm just trying to so this will be group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8, right? Something like that now. So I have something like this, right? Remember that all these parts don't supposed to be here, right? So I'm just trying to boggle everything together. So just be able to understand it. So this is exactly how the periodic table is all about, right? This just a glimpse of how it looks. Don't mind my drawing. So in this part we have like two sections. Let me draw the sections here, right? We have like another two row under this periodic table, right? I get it. You see these two first row, that is the alkaline metal and the alkaline earth metals. They are known as what? This representative element. Do you understand that? They are known as what? Representative element. And why are they known as representative element? Because what? This part is known as the what? S block. You get here is known as what? The P block. Here is what is contained here? Transition element. What of here? What are they called? I'm sorry, here D. Sorry, please cancel it. D. Here's D, right? Why here is what? The P block. This is the transition element. These are the what? Representative element. These are the P block elements, right? And all of this, the lactinide and actinide series, and they are known as what? The F block. They are what? The F block. Do you get the point now? So the valence electron in this part are found in which orbital? The answer is they're looking at you already. This. But now, why are they called the S block? Because the valence electron, the last electron are found what in the S block. Now let me just give one example. So we just kind of round up. I think we have like one more question left. Okay, so now look at this. It's actually very simple. Let me use sodium, right? That is 281, right? But this does not give us a very good example. So I'll use the electronic configuration, which is 1s2, 2s2, 2p6, and 3s1. Right? So look at where does the valence electron lies? It lies in the s subshell, right? It lies in the what? S subshell. Do you get that? So sodium will be definitely here, right? Because of here signifies the period, while here signifies what? The group. This signifies the group, the first group. It will be in the first group, right? And S signifies the block of the periodic table it's at. Do you understand that? So thank you all for being here, right? I really appreciate. Consider subscribing to this channel, right? We will definitely bring you more and more interesting video from now henceforth, right? Ensure you subscribe, and I'm sure you understand it perfectly, right? I'm sure you understand it perfectly. Thank you so much for being here. Have a good day.